This is about understanding opacity in machine learning model. Opaque means like not transparent. As we know that the models that we are building are going complex day by day. So it's like it's the interpretability of the model is becoming a problem. So in this talk, we'll be covering these things: the context and motivation of model opacity, real world use cases, why we need interpretability or removing the opacity in models, understanding interpretation or opacity, type of interpretation, scope of interpretation, and then some demos and examples. Okay, so I'm Ankit Rathi. I have around 14 years of experience with me, mainly into data and analytics. I'm in data science and AI field for last 6 years. And Yatin Bhatia, he has around 13 years of experience and around 7 years in to data science and AI. So let me set the context and start with the story. Um, so you know this plane, right? Boeing 737 Max. So it has crashed 2 times because of, it's like the root cause is MCAS, complex software system, and now it's like the fixes are being made. Okay, and it is not, the MCAS is not typical AI system. It's a semi CI AI, you can say, where it's like we have programmed a software based on some sensors, and it's like somewhere in between things have gone wrong. And so the human nature is, if everything is going fine, we are cool with the machines, right? Like, but something happens, then everybody wants to know why that has happened, right? So basically, it's like we want to understand if some decisions have been taken by a machine, then it's like why those were taken. And this is, it's like that is what this presentation is all about. It's like as the models are going complex day by day, business wants to understand why it's like some models are behaving that way, and government wants to understand. So it's like everybody wants to know, yet having the accuracy in place, but also wants to understand it's like why the models are behaving a particular way. Yeah. Okay. So in the last decade, machine learning and deep learning, the overall AI landscape has evolved from the lab to the industry. Now, basically, we are working in applied AI. Research are going on, but whatever research have been made, it's like we are applying to different use cases in the industry. And for the applied AI, the effective application is paramount. Basically, it's like, yeah, whatever decisions are being made by the models, it's like those should be effective in a way that the human should be able to understand it, and it's like if rectify whatever is the problem with the decisions, if there is. So this is the joke in machine learning industry. It's like the model work in a way where we keep manipulating the data unless it provides the result that we require. So basically, we just we treat the models, at least the business treats the models as a black box model, and we just shuffle the data and expect the result. And if we are getting the right result in the desired accuracy, then we say that it's like models are performing fine. So MLDL models learn patterns and relationship from the data itself. Now the challenge here is, whatever models have learned, how to explain that to the business. First thing is that. Second is, there are some regulatory requirements as well. If you have heard about GDPR, it's like the government want to know, it's like if we are denying loan to somebody, why we are doing that. Or maybe certain the autonomous cars are coming into picture, then ethical concerns are, it's like being raised, it's like how the models will behave. Um, so again, typically without machine learning models, we used to instruct machines in sequential model or sequential patterns, and it's like they used to take decisions which we knew, it's like why a particular decision has been made. But with machine learning, it's like we are feeding the data to a machine, and on its own it is learning the patterns and making the decision. So we need to understand, it's like the transparency that we had, it's like we were giving the instructions, the control we have over the software programs, it's like we need similar kind of control over the programs in the different era where it's like machine learning models are being applied. So now model interpretability, as I mentioned few reasons that it is important, it is becoming important, and after that the interpretable models have their inherent problems as well, like when we use linear models, those are highly biased, means like we can't move beyond a certain accuracy if we use linear models. If we use tree based model, then we have high variance if we try to tune it too much. So point is, means like different models, we make certain assumptions and we have certain restrictions as well. So inherent problems with the models are there, and we need to basically choose one of the model or maybe many of them to make a business work. This often leads to the sacrifice in performance. So when basically we try to make the models more interpretable, then accuracy goes down. It's like I'll show you a graph in a moment, but again ultimately it boils down to the interpretability versus performance. As you can see that it's like here if we use simpler models, our interpretability is high but the accuracy may be low, and as we start using complex models, it's like the accuracy we improve on but the interpretability goes low. Now how much interpretability and accuracy is required, that is a business question. But again in many cases, as I've mentioned, it's like we can't trade off the accuracy with the interpretability because it may be important for certain business cases. So few of the use cases I've mentioned here where you can realize that it's like the interpretability is more important, like predicting potential criminals. So if I'm saying that you are a criminal, it's like a law enforcement agency is saying, it's like they need to, and a model is saying it's like you can be a potential criminal, then we need to explain it. Credit scoring. So it's like if your credit score is low, then it's like, and one morning you get to know that your credit scoring is low, then you would like to know why it's like that is low, and you need, it's like if you ask your bank or maybe the authority, they should be able to explain it to you. Fraud detection. So if one of our customer is fraud, it's like our model has told so, and we need to maybe explain the customer, he might want to know the reasoning why it's like he is being targeted, or it's like what actions he has taken, that it's like so the interpretability is required to him as well. Health assessment. It's like if it's like your health data is being provided to a certain model and it says you have cancer, then it may need more, you would like to find out it's like some maybe specific details about your, it's like why you have been diagnosed with that particular disease. Loan lending. It's like again, it's like if the loan has been denied to a particular customer, then he would like to know it's like what are the reasons. And even like the law enforcement, like GDPR, it's like force you to do so. It's like it has started in some certain countries. Now let's come to the interpretation. So model is basically a response function. It's like if we look at what we are having is, we have independent variables, and then we try to basically out of a function we try to respond a variable. So basically a model is a response function, and what we are doing is we are basically it's like tuning that function to give us near correct output. Now the interpretability is like is basically understanding that response function, how it is working, and there are certain aspects like what drives the model prediction, means like how fair your model is, why did model take a certain decision. So means like this is related to means like how your model is faring, and why the model took a particular decision is basically means like if you have certain amount of data and on a particular data point, if a model has taken a decision, why that has been taken. Now how can we trust model predictions? So that is the about the transparency. It's like overall model is performing and it is giving the prediction, but on the overall data points, it's like how fair it is, how transparent it is. So those are the questions that we try to answer as a part of model interpretability. Besides model performance, human understanding is important. So as I mentioned, it's like accuracy is not everything. In many cases, it's like it all depends on apart from accuracy, how interpretable your models are. So there are segregation has been done for model interpretation based on their types. So intrinsic versus post hoc is basically means like certain models are more interpretable in nature, like the linear models. You build a kind of function, and when you build function, you have a simple line or at least some kind of form where you can understand how your model is behaving. Maybe a decision tree as well. It's like you can see them. It's like how the bifurcation has happened across the tree. But it's like when you ensemble certain models, or maybe you use neural nets, then basically it's like those are post hoc. Those models are not intrinsic. On an intrinsic level, they are not able to explain why the models are behaving in a particular way. So you need to use a kind of post hoc method. You need to apply something over and above that model to make it more interpretable. There are several techniques we'll be covering later. Model specific versus model agnostic. So there are certain techniques which work on particular models only, like the decision tree or random forest. Means like we can generate the feature importance, but on neural nets or deep learning, means like we need to apply something. So generally we use in those scenarios model agnostic ways to interpret those models. Local or global. So basically, when we are trying to explain our overall model, then we say that it's like those techniques are global in nature. But if we are trying to explain a particular decision taken, it's like out of 100 customer, if we want to understand for a particular customer some decision has been taken, and we are trying to understand that is a local interpretability. Each has its own pros and cons, and generally we use mix of techniques to explain the interpretability on a model level and an instance level. So this is the one of the as I mentioned, when the model is complex, you treat it as a black box, but you have the real world. You just convert whatever you see in the data. You build your models, maybe simpler one or the complex one. If it is simpler one, then it has some inherent technique to understand that model. But if it doesn't, then you apply some of the interpretability methods over it, and then basically it's like human can interpret that. So this is the chain of the model interpretability. Now the scope of model interpretation. So we have already covered means like global interpretation is basically means like how a model is behaving overall. Local interpretation is we are trying to understand why a particular decision is taken rather than the overall model. And model transparency is how your model is behaving for each model, because each model has certain properties. So like linear models, in model transparency means like if we are applying a particular technique, then we would try to know the coefficients. If it's a tree based model, then we need to know means like how the split has happened across the nodes. If it's a deep learning model, then we would like to understand what is the weight on a particular node. So model transparency talks about that. So I'll be handing over to Yatin to proceed from here. Yeah.
Yeah. So I can continue on with the remaining slide. So this slide GDPR. So this thing model interpretability. It is your option actually, your choice. But somewhere it is like law. According to law, you have to give. So what GDPR says in this article 13. So like if you are my customer and I am using your data actually to recommend you something, you have every right to ask me questions like how it has happened. Like GDPR applies to all the European country. So now there it is a law actually. You have to comply with that thing. There is no option. remaining US, India, there are options, but there it's not an option. So we have to regulate by the law. So this is necessity by the law. We have to do this thing. We have to bring it in the culture. Now, other thing is model already has a bias. That again became a necessity to like you should interpret your models. For an example, so this is output of the word to vec. On top of word to vec, somebody has run like if man is to computer programmer, then woman is to what? Answer are surprising. It came as homemaker. It came as housewife. Model is already racist actually here. So if you are predicting on top of this model, so you are already doing a bias. User has every right to ask the questions because you already have a data which is biased data. So you should encounter these things. So there are ways to encounter, like to correct these things in the word-to-vec model actually. Something like you are analyzing on top of like whether you are suggesting someone is a criminal or not. But here it's already written like again word-to-vec surprises us. Maximum similar words are illegal. Legal immigrant. Model is already biased. So you need to first correct your data. So again, a question can be asked by the user that your data is biased. Then how are you giving me the fair prediction? Again, a necessity actually. Yeah. Then Kagglification. So the point here I want to make is, in Kagglification we do Kaggle. So that's good thing. We make a lot of money also. So that's all fine. But in business that doesn't come true because business wants 70% accuracy and a very good interpretation. So things are actually what Ankit has also explained, actually reverse in the industry. Whatever we do in the Kaggle, in business it does the reverse because they are the business leader, they are working for 15, 20 years. They want to understand the output of each and everything. You are saying somebody has a cancer, just give me the, just give me the proof of it. For everything they want the proof. So there you can't have an ensemble of models, then stacking, then 50 models give you not 96 but 99.3. That's not required actually in the business. So that's the point I want to quote here. So we have some ways to sort this out. So one is this Shapley values. So you have the data, you build your machine learning model, you do the prediction, right? This also is a machine learning model, but this is a complex model. It uses this data and this model to build an interpretable model. So using the current model and the current data. When you give the prediction, then you can use this Shapley model to interpret your things. Whatever complex thing you have done, complex model you have made, ensemble and all, it will assist you with some interpretation also, the same thing. So a lot of explainers are available. So it's not like for every model you are building some RC and then every model it's not there yet that you are getting explainer for each and everything. But the things have started, they are actually providing interpretable for linear regression, then some kernel, then from tree-based model like XGBoost, random forest, it's available. Then deep learning to some extent, but it's not like that each and everything you can interpret, but to some extent it is there. Yeah, so the procedure is something like suppose for some data set I, and you have some feature, you want to know the relevance of this feature in your prediction. So it uses some Shapley values based on game theory that you will take a subset in which this particular feature is not there. All the subsets in which this particular feature is not there. Now what is the impact of these features in the models built by those subsets? You will get that particular feature response, and you will ultimately get that particular feature importance for all these models built on the subset. So for each particular input data actually, and so you will get the importance of every particular feature actually. Something built on the game theory. This is LIME, another interpretation algorithm. So what it does is, when you have something like data and prediction, you predict flu. So it will give you something like some of the diagnosis, like you have the sneeze, headache, and that proves that you have the flu. Well, how it does it? So suppose you have a very complex model. What it does is, and this you will take one particular data element. You want to know, so you are giving that it is cross red. Why it is cross red? Why not blue circle? So it will build linear regression model close to it. It will take just samples close to it and build a linear regression equation. Linear regression, and they are very easy to interpret. You get the theta 1, theta naught, theta 1 values. So they are easy to interpret. So complex model reduced to linear regression, then you can interpret. Like here, for age of 20, and here it's y-axis, it's the probability. Age of 20, probability of cancer is less. Age of 60, probability of cancer is high. How are you doing it? It's a complex model, but in the linear regression, it is like taking some points close to it, drawing a line. Now, interpreting theta naught, theta 1 values are simple, actually. They are simpler to understand. So, converting a complex model to a linear regression, actually. That's how Lime does it. So, we can, I have taken a data set, Boston housing data set. The task is to predict the value of the house based on a lot of parameters. Something like lower status of the population. How many percentage is the lower status of the population? Lot of parameters are there. We can just. So for this data, Boston housing data set. So this is the global interpretability. I think a lot of people are already using this thing, feature importance thing. But you don't know that this is also a part of modern interpretability, because globally at the model level you are giving at least which feature is important, which is not important. So this is from the sklearn gradient boosting library. Then, yeah. So this is the shape values. Shape values give the local interpretation as well as the global interpretation. So they can also give you the list of which are the values which are important, which are not. This is again a shape values, but the plot is something like for every prediction, every feature you are taking the importance of that. Yeah, no, this is important actually. This is shape values. You have taken a particular prediction. You have predicted this thing to your customer. Customer wants to know why you have predicted this thing. Something like you have predicted this score 22. Why you have predicted this thing? So we have to interpret it. We have to reason it. We will reason it by using shape values like what we have described, like converting from a complex to a less complex model. And so here what I have given is, so you will not just give this value, you will give some bars actually. Like these represent the higher, because of these features present in this particular input data set, my values goes higher. Something like my percentage of people which is like lower standard. So median value or mean value is 11.3, but my value is 7.34. Percentage of lower people for this particular area is low. So that's why my housing price is higher. Just a reason actually. Okay, LSAT just like it is described like why it is higher, because this feature makes it higher. Yeah, this is the, okay. So this is the Lime. Lime is somewhat less algorithm agnostic, but it is more explainable. It is giving you that LSAT is in this particular range. That's why I am giving this particular prediction. It is giving you more information as compared to SHAP, but SHAP values are more, the more algorithms are there in the SHAP values. Lime is slightly simple, but explanation is more in the Lime. So now the point is in this slide is to inculcate more modern interpretability. How we can do more modern interpretability? Something like we can introduce in our daily practice, blog posts, talks, we can write more. Because as a data scientist, our task is to teach or make the business community learn about this thing, so that they can more rely on us. They can more like whatever we are saying, they are more assured of our thing. And something like we not need to get away from Kaggle, but also doing this thing. And so one more thing is, one more metric we can introduce. Like to our customer, we say like for our model, the F1 score is this, accuracy is this. Just introduce one more metric, like model interpretability. So you are saying your model is 80% accurate and your interpretability is 90%. That gives more assurance to your customer actually. Instead of like your model is 90% and your interpretability is 30%. So just introduce this one more metric.